Let us now introduce random variable. So what is a random variable? So random variable is nothing but a function. So it is a real valued function defined on the sample space. So you denote it by capital X. You could have also denoted it by F, but in probability you denote it by capital letters. It goes from the sample space omega to real numbers. That is why it is called real valued function. Now it has an important property that the domain it acts on lies in a sigma field. So that is function x acting on the small omega. The small omega is part of sample space, and this x of small omega less than equal to this small x is nothing but a real number. So basically this means that we are just choosing the part of the domain of the function, and this domain is part of the sigma field f. Now this is important because when you apply a probability, you apply it on a sigma field. You generally do not apply it on the entire sample space. So again, for each this small x part of real numbers. So let us do some examples. So say you have simple coin toss, your sample space is head and tail. So you can define a random variable x1 as x1. If you get head, it takes on value 1. If you get tail, it takes on value 5. So let us just draw this. So again, you go from omega to real numbers. So the random variable will go from sample space and take you to real numbers. So in the first example, our sample space consists of head and tail, and the real numbers are 1 and 5. So x1 acting on head gives you 1, and acting on tail it gives you 5. So this is random variable x1. Now in the same sample space we can define another random variable x2. So x2 of head say is -1, x2 of tail is 1. So again you go from sample space omega to real numbers. Again say you have head and you have tail, and the real numbers now are 1 and -1. So you have 1 and you have -1. So x2 of head is -1. So head gets mapped to -1 and tail gets mapped to 1. So this is random variable x2. And similarly you can have x3. x3 of head goes to √3, x3 of tail goes to 0. So basically random variable act on the sample space and take the sample space to real numbers. Another example, so they say you have two coin toss, head head, head tail, tail head, and tail tail. So again say there is a random variable y which denotes the number of heads. So again let us draw this sample space omega, and you will end up in real numbers, and our random variable is y. It counts the number of heads. So you have head head. So head head gets mapped to 2 because it is 2 heads. Head tail and tail head both have 1 head each. 1 head here, 1 head here. So both of them will get mapped to 1. And then you have tail tail. So this is 0 heads. So it gets mapped to 0. So notice that in real numbers you also have numbers like √2, √3, you have -1, -2, and nothing is getting mapped to it, but they are there in the real numbers. Similarly here you had 0 here, but nothing is getting mapped to 0. You have 0 here in real numbers, nothing is getting mapped to 0. So this you need to keep in mind, that real numbers are really big, but this random variable is just acting on some parts of the sample space and taking them to real numbers. Now on the sample space you also have probability acting on it. Probability itself can be called a random variable. So probability, for example, now probability function, this goes from omega to 0, 1. the interval, and this interval lies in the real numbers. So for example, associated with head, you get half for a fair coin, and if probability of tail is also half. So if you have the probability function acting on the sample space, you get half here, and that is precisely what we are going to use. So when x1 takes on value 1, so this 1 is also associated with head, but probability of head is half. So probability that x1 takes on value 1 is half. Probability that x1 takes on value 5 is same as probability of tail, which is half, because this probability function is acting on the sample space too. Just like random variable is acting, you have probability function acting. So again, since random variables have sample space as their domain, we can associate probability p with them. So, but p acts on sigma field. So we have talked about this before. The probability acts on sigma field, and that's why you need this condition right here. So this condition is needed because you have to associate probability with the random variables, and therefore we need the technical condition. So first example is clear. For the second example, again, you have the same thing. So with random variable y, you have to associate a probability function. So for the probability function, again, you can say that you have to draw the probability for the corresponding random variable. So probability will also act on omega and will take you to the interval 0 to 1. So first look at head-head. What is the probability of head-head? Probability of head-head is 1 by 4, because you see sample space consists of head-head, head-tail, tail-head, and tail-tail. So head-head probability is 1 by 4. It is one event. So probability that the random variable y is equal to 2 is same as probability of head-head, which is 1 by 4. Probability that y is 1. Probability that y is 1, this is associated with two events, head-tail and tail-head. So probability of head-tail, probability of tail-head also gets mapped to 1 by 4. And probability of tail-tail also gets mapped to 1 by 4. So here, probability that y is 1 is associated with these two events. So you add up their probabilities. Probability of head-tail is 1 by 4. Probability of tail-head is 1 by 4. You add them up, you get 2 by 4. Probability that y is 0, that is, it is associated with tail-tail. Y goes to 0. So probability of tail-tail is just 1 by 4. And that is it. So we have been able to construct random variables and then associate probability with them.